This amazing metamorphosis has earned concrete the nickname liquid rock. It has served as a cornerstone of engineering for centuries. And it's a highly prized tool of construction for a reason.
It's easy to take concrete for granted. People see it in sidewalks and roads all the time, every day. But in fact, it is the closest thing to a miraculous material in construction that we've ever had.
Concrete is everywhere. It has an almost unlimited engineering potential. It can take on nearly any shape and forms the backbone of a variety of the world's construction. Superhighways, massive bridges, man-made waterways, mega dams, the world's tallest skyscrapers. This miracle material begs the question, how does it do it all?
I worked on a lot of jobs, and basically they all have a different formula for their concrete. Now, I can't imagine, the world without concrete.
The basic formula for concrete is simple. Sand, crushed rock, called aggregate, water, and the heart of the concrete mix, cement.
Cement, it is the grey, powdery material that acts as a glue that sticks all of the concrete together. It covers and coats all of the gravel, the sand, and the rock as a way of gluing and binding the whole material together.
To make cement, you need limestone, clay, and other elements like iron. These ingredients are crushed and combined into a powder that's poured into a kiln. The massive cylindrical spinning kilns heat the mixture to a temperature as high as 2,700 degrees Fahrenheit. The mixture becomes partially molten, forming a new marble-sized component called clinker. Once cooled, machines grind clinker into a superfine powder we know as cement. Cement binds the ingredients together. When added to sand, water, and crushed rock, the cement reacts, linking the raw elements into one powerful whole. Water is the key. When cement reacts to the water, it undergoes a transformation called hydration. During this reaction, a node forms on the surface of each cement particle. The node grows and expands, linking up with other nodes. It sticks to the crushed rock and sand in the mix. Cement binds these ingredients. As it solidifies, concrete becomes a building block of modern construction. This basic process hasn't changed in over a century. But creating concrete is no simple matter. Making the right recipe requires precision and flawless preparation. It is a synergy of ingredients and timing.
In a way, making concrete is like making a cake. There are lots of different recipes to make a cake. You get different flavors, different colors, different textures, but there are also lots of ways that you can make a cake wrong. It's not going to set properly, or it can come out in a way that's very different from your intentions.
Getting the recipe right is everything, and the consequences of a flawed mix can be deadly. The residents of Mexico City learned this the hard way. On September 19th, 1985, the Mexican capital is rocked by an 8.1 magnitude earthquake. It causes up to $5 billion in damages. Investigation of the rubble reveals that many of the buildings had been made of a substandard concrete.
Yes, we saw examples after the Mexican earthquake where when you use inferior concrete and you skimp on the rebar, and we saw both extensively in Mexico City, the concrete doesn't have its expected strength. The result is walls would fracture and shear and the building would collapse when the expectation would have been that the building should have easily survived to preserve health and safety.
The consequences of this quake are tragic. An estimated 10,000 die. Another 50,000 are injured. But with the right formula, structures made of concrete can endure thousands of years. Although other civilizations, including the Egyptians, experiment with concrete, the Romans transform it from a supporting material to a main substance. In Rome, liquid rock fuels the dreams of an empire. The word concrete even originates in Rome. From the Latin concretus, it means grown together or compounded. Roman concrete contains the traditional ingredients of sand, water, and crushed rock. But volcanic ash from the hills of Pozzuoli, Italy, transforms the material.
The Romans were very astute architects and engineers, and they recognized that by mixing volcanic ash from Lake Pozzuoli in Italy, they were able to get a concrete that became very hard.
This volcanic ash proves to be an adhesive binding agent. It gives ancient Rome a powerfully strong concrete. This innovation allows the Romans to craft an empire from the ground up. Concrete becomes the backbone of a dizzying array of structures, aqueducts, bathhouses, and markets. But today, one structure alone stands as a unique testament to the power of ancient Roman concrete: the Pantheon.
The Pantheon is one of the great architectural works of ancient Rome, with the wonderful colonnade that introduces the building, and then a huge drum covered by this amazing 142-foot dome, and that dome is made of concrete.
Constructed around 125 AD, the Pantheon has stood prominently in the center of Rome for over 1,800 years. It is one of the world's oldest buildings in continuous use. This former temple to the Roman gods combines elements of engineering and design, and nowhere is that more apparent than in this concrete dome. Stretching 142 feet in diameter, it is the largest surviving dome from the ancient world. It was the largest dome in Western Europe until the 15th century. Unlike modern-day domes, which are generally reinforced, the only material holding the dome of the Pantheon together is Roman concrete.
Constructing an unreinforced concrete dome on the scale of the Pantheon is just an incredible engineering achievement. You couldn't do something today because everybody would have praised the odds of your success as so small as you would never get a chance to do it.
The dome of the Pantheon is a stunning example of how Roman concrete could be built to last. Each layer of the dome becomes less dense the closer it gets to the top. At its weakest point, the Romans designed an oculus which reduced weight and stress. These innovations continue to impress engineers almost 2,000 years later.
For 1,500 years, that was the largest dome ever built by man. There aren't many engineered structures that stand that kind of record of time. And then all the countless use the Romans made for engineering aqueducts and other structures, roads, that made their civilization come together. So it's very difficult to imagine the Romans without concrete technology.
The Pantheon's one-two punch of engineering know-how and architectural innovation influenced many structures to come. Thomas Jefferson's Rotunda at the University of Virginia, the Low Library at Columbia University, but none comes close to the Pantheon's lasting power. With the fall of the Roman Empire, concrete is relegated to a supporting role. It is no longer the building material of choice. All that remains is the engineering brilliance of the Pantheon and other Roman structures made of concrete. Nearly 2,000 years later, builders would ask an almost impossible question. How do you conquer the land mass between two oceans? It holds more than 52 million gallons of water. It cuts a path straight through the heart of a nation. It is safely navigated by more than 12,000 ships every year. The Panama Canal. It's not one of the world's great rivers. It's an entirely man-made waterway. And the material that controls this much water is liquid rock, concrete.
By the late 19th century, the idea of a canal connecting across the isthmus somewhere in Central America had been floated for some time.
Before its construction, a trip by boat from New York to San Francisco meant sailing 13,600 miles and crossing through the deadly waters of Cape Horn.
The importance of the Panama Canal cannot be underestimated because before it existed, oil shipping had to take place between the Atlantic and the Pacific Ocean by going around Cape Horn, which is very treacherous, very severe storms for many months of the year, and many ships have been lost.
The massive storms along the Horn had been sending skilled sailors and precious cargo to the depths of the ocean. The world needs a better route, a safer route. February 1st, 1881. Ferdinand de Lesseps, the architect who crafted the Suez Canal in Egypt, decides to build another waterway through the country of Panama. Standing in his way are 51 miles of dense tropical jungle, torturous heat, and the fortress-like walls of Panama's central mountain range.
How do you cut through the Continental Divide? Unfortunately, they hadn't talked to the rock. If the devil could have designed a material to plague poor de Lesseps, he would have made this material. As soon as you expose it to air, it oxidized. You'd excavate, and it would slide in. It just ended up to be just an impossible project.
De Lesseps' Panama Canal project quickly meets with disastrous consequences. 22,000 workers die due to landslides, tropical disease, and dynamite. After 8 years, the French abandon the canal project. But the French failure is not simply due to disease and the mounting death toll. From an engineering standpoint, their plan is flawed. With the American economy booming, an ambitious young nation takes over the canal project. President Teddy Roosevelt decides that U.S. workers are up to the task. American engineers learn from the French mistakes. The French tried to carve out a sea-level route through the difficult terrain, just like the Suez Canal. Instead, Americans use a series of chambers known as locks.
Locks are simply big concrete tubs that you put between two bodies of water that have different elevation. You put a concrete tub between them, and the tub has got to be higher than the highest water. And then you put doors on each end of the tub, watertight doors.
These chambers with doors fill with water, allowing ships to rise in steps. The ship crosses an artificial lake, then descends along a series of locks to the other side.
It's just a concrete tub with doors on each end that raises things from low water to high water, or the reverse works just fine. You open the high water end, sail in the ship, close the doors, turn on the pipes down here, the ship settles down to the low level, open those doors, and off you go.
With enough concrete, they hope to dam the Chagres River. By redirecting the river, they will feed the artificial lake and fill the locks. And the best option for the locks is liquid rock.
Without concrete, the Panama Canal would have been almost inconceivable. Certainly canals had been built before that. It's something that could be done, but at the scale that we were talking about, especially with the goals that they had in terms of timing, it would have been very, very difficult to do that without concrete.
The concrete locks will be a stairway bringing ships to the level of the lake. But they will need a high-strength concrete that can hold 26.7 million gallons of water for each lock. That's the equivalent of over 40 Olympic-sized swimming pools. Construction begins in 1904.
About 4.5 million cubic yards of concrete were used in the construction of the Panama Canal. And because so much concrete was needed, they had to set 8 on-site batch plants in order to produce that